We'll start off with this really simple case. In fact, this may be simpler than any perceptron model you've seen so far. We have one input variable, we have one output variable, and just one intermediate step. And let's suppose that the output layer that we want is binary. So something that is a 0 and a 1. And our input layer, let's just assume that that is continuous. Now, we're just feeding in one variable, but that doesn't mean we're only feeding in one observation. What I want you to think is that we may have, let's say, a column of data, which we'll call x1, but it may have, 100 different observations. Let's suppose this was the weight of a car, and and so maybe the car is, I don't know, I'm not sure how much cars weigh, 5,000 pounds, 4,000 pounds, 4.3 thousand pounds, and so forth. And since this is a classification problem, what is it we're classifying? Let's suppose that the y that we're trying to predict here is whether the car is foreign or domestic. So this is going to be a bunch of zeros and ones and so forth. All right, so the first thing we need to do is feed in our data into our model. And let's just presume that the weights, and we're also going to have a bias here. So the weight and the bias, let's just say that we already know those numbers. We're not going to mess with the perceptron update rule right now. Let's just presuppose that the machine has already done its learning and it has workable parameters, the weights and the biases. So what do? Well, this should be familiar by now. We feed the data in, and we just feed it in one observation. So we just feed in the 5,000, and then what? Well, we're going to take this value of x, that's here now in the green dot, the green node. We multiply it by its weight. So that's W1 times, what was that, 5,000. I don't know what W1 is, just some number, could be 2 or 10 or whatever. We'll add the bias to that, and we'll call this Z. And for perceptrons, our rule was if Z is greater than 0, then our prediction for Y is going to be 1. And if Z is negative, it's less than 0, then we're going to predict 0. Maybe this is domestic and this is foreign. So we'll get an output. We'll get this Y hat, and hopefully it's the same value as that was actually the case. If not, then maybe our model needs some tweaking. We need to update those parameters. Again, notice that even though we only had one input, we could have 100 of these observations. In fact, you could have millions of them. If our weights and biases are good, then we can feed it any old weight, any old x1, and get a pretty good guess on whether it was foreign or domestic. I just realized, by the way, that I'm using weight in two different ways here. I'm using it as the weight of the car, and I'm also using it here as the parameter value, the weight of the node. Apologies for that. So, all right, so visually, what's going on here? I actually have data on cars, on their weights and whether they're foreign or domestic, and I've plotted them. This is data from 1978. And this was a period of time when American cars were mammoth, like behemoth cars, or boats on wheels. They're really heavy. And imported cars, like from Japan, were very tiny, very light, very fuel efficient. And so you could actually do a pretty decent job of figuring out, like if I told you the weight of a car, you could tell me whether it was foreign or imported. If it was super heavy, it was probably an American-made car. So a perceptron model would try to ideally find a perfect line of demarcation so that to the left of that line, we're predicting imports. And to the right of that line, we're predicting domestic car, U.S. cars. So we're predicting the one. And we've conceptualized this as trying to find a line that splits these two. But notice it's also, like if you think of the entire function, it's also a line that fits the data really well. Now in this case, there is no one line that perfectly splits the data. We say that the data isn't linearly separable. Now that is a problem for the perceptron model, kind of like the XOR problem. For now, let's just say that one workable solution would be, rather than having a step function like this very sharp S-shaped curve, that if z is less than 0, if it's bigger than something, 1, to have kind of more of a softly sloping S-shaped function rather than that sharply bent one. Something like this. And in fact, this curve in statistics, it has a name. It's called the logistics curve. It's an S-shaped function. If I had cars that were even lighter, you would see this line kind of asymptote like that. So it's an S-shaped function. It's kind of like the S, the step function that we did, but it's a little bit more smoothed out. Now that kind of function works really, really well. We'll actually talk a whole lot about different kinds of functions like this, where they add some kind of nonlinearity to our model. The z part was weights and biases. That part was linear, but then we had the if the z is bigger than something, then guess 1. If it's less than 0, guess 0. This thing is a nonlinear function. And we're going to get to play around with different kinds of nonlinear functions that'll help us fit scatters of points and predict functions a little bit better. For now, just appreciate that a one-dimensional model can give us a whole lot of interesting information. If we have a continuous x and a binary y, for the most part, a perceptron model will do pretty well. We can generalize beyond this, though, and we'll see how to do that here in just a moment.